Welcome to the course of data science. In today's lecture, we will talk about data pre-processing. This is unit number 2.3. Data pre-processing is a very important concept, and it is also a very important step in data science. Before going into the further details or the next step in which we have to develop some models and then test the models and visualization or many activities like this, we first need to perform pre-processing, because pre-processing ensures that data is in the desired format and all the ambiguities and issues are already removed prior to the actual process, or prior to the model in which we are actually interested. So data pre-processing is one of the most important steps in data science. If you ignore this step, if you directly jump into the next phase of the data science or the next phase of the data science pipeline, then you miss an important step and an important opportunity, because data pre-processing provides you an opportunity to fine-tune your data so that all the ambiguities must be removed, and then your data is ready for further processing. For example, there are many issues like incomplete data, when some of the attributes values are lacking, certain attributes of interest are lacking, or attributes contain only aggregate data. So missing values or lacking values is a simple thing, that one or more attribute in one or more record does not have a value. But when we talk about aggregate data, means you have missed the detailed data and somehow you combine multiple records or multiple values to create an aggregate. In that case, you might need to be interested in getting detailed value. So in incomplete data, you have either missed values or missing values, or aggregate data means you have a aggregated data which you have created or somehow you have got from a source which actually combine multiple values from multiple records or multiple tuples to create that particular aggregated value. However, it will be great if you have a detailed value at the lower granularity. Other than that, you might have noisy data when data contains errors or outliers. What is outliers? For example, if we just talk about age of a person, okay? So it might be, or it may be from 0 to 70 or 80 generally. It will be like maybe it is possible that a human have basically an age of 100 or maybe 110 or 120. Okay, but in most of the cases the age generally from 0 to 80, and if you want to include even 100 or 110, it's okay. So let's create a range, maybe 0 to 100. But what about if your age attribute contains a value of 240? So in the current time period, it is almost impossible to have a person of age 230 or 240 or something like that. So there might be the reason that this value is actually a wrong value. It's an outlier. Okay, because it does not belong to the values of this particular attribute. It's somehow maybe maybe when someone is actually entering the data might have entered a wrong data, or might be due to some other reason it got a wrong value. So this is outlier. And of course, due to outlier, it actually corrupts your data. Okay, so it actually create problems during creation of your model. So that is why removing outlier, identifying outlier, and then of course removing outlier is a very important thing. Okay, so this is one of the reasons. Other than that, definitely maybe if in a gender, like you are having value of male or female, but somehow basically someone has actually entered XYZ, so it should not be a gender. This is another example of error which belongs to the noisy data. Okay, so there another reason maybe inconsistent data, which actually data contains discrepancies in codes or names. For example, if the name columns for registration record of employee contains values other than alphabetical order, or if record do not start with a capital letter, discrepancies are present. There are many reasons of discrepancies. Okay, so in general, it is impossible that a person name contains a numeric value or a special character, like Amir $1. It is impossible that a person have this type of name. So this might be possibility that again, while entering the data into the system, someone has basically entered wrong data. Okay. These are the reasons. So in general, we can categorize the problem associated with data in 3 categories: incomplete, noisy, and inconsistent data. And in order to basically perform the next phases of data science, we need to ensure that we must have performed data pre-processing. And without doing data processing or data pre-processing, it is not recommended to move to the next phase of the data science. Okay. So with this, now we have an understanding about it, that why data pre-processing is required. Data pre-processing is required because of the issues like incomplete data, like noisy data, and like inconsistent data. Okay. So let's move to the next slide. So how we can deal with it? How we can deal with these problems? What are the problems? Incomplete data problem, noisy data problem, inconsistent data. So how we can deal with these problems? In one word, we want to clean our data. We want to purify our data. We want to eliminate all these inconsistencies. So how we will clean our data? Broadly, we can put data cleaning into 3 different types. Number 1 is data wrangling, number 2 is handling missing data, and number 3 is actually smooth noisy data. So what is actually data wrangling? Sometimes we call it munging. Data wrangling or munging are the same thing. Okay? Actually, sometimes data is not in a format that is easy to work with. Means the given data is not in a format, not in a structure appropriate to work with. So what you can do it? You have to perform data wrangling. You have to convert data into another form, another structure, which must be appropriate for data analysis. Okay. So what we are doing here, we are actually converting data from one structure or one format to another. Why? Because the actual or the source data is not very appropriate for analysis or not very appropriate for data analysis. So we are actually doing conversion or conversion into another form so that it become more appropriate for data analysis. Okay, so converting from source to the desired format or desired structure is actually data wrangling. Let's take an example. Here, consider the following text recipe. This is the data given to you. This is a source data. Which one? Add 2 diced tomatoes, 3 cloves of garlic, and a pinch of salt in the mix. Actually, again, it's a free form text. Okay, you and me can very easily understand that what we have to do. But how we can transform it into a appropriate form that will be fine or that will be recommended for data analysis. So you might convert this data into a tabular structure. Source this, and you are converting tabular structure like this. You have wrote or you have created a table like this structure: ingredients, quantity, and unit size. Okay, so tomato, cloves of garlic means garlic, okay, and basically salt. Okay. So 2 diced tomato, the quantity of tomato is 2, unit is diced. Okay, 3 cloves of garlic. Okay, so the ingredient is actually garlic, quantity 3, and the unit is 3 cloves. Okay, you know it very well. In garlic there are many cloves, so you just remove 3 cloves from the whole garlic, and a pinch of salt in the mix. So salt is an ingredient, and one, and just 1 pinch. Okay, so what we have done here, we have transformed your data from one form to another form, from source form to the desired form. The desired form is actually is more appropriate for data analysis. Here it is very important to mention that there is no specific approach or systematic approach. There is no specific technique through which you can actually perform data wrangling. However, you have to try, you have to decide, you have to perform your own method or strategy to convert data from source format to the desired format, or desired means a format which is more appropriate for data analysis. So this is data wrangling. Let's move forward. Handling missing data. So what you will be doing in case if some data is actually missing? You might have basically one or more column in which some of the data is actually available, but for rest of the cases data is actually missing. Means you might have thousands of records or thousands of tuples and having maybe 5-10 columns. In some of the columns, for some of the tuples, the value is actually missing. So if the value is missing, when you will be building the model, or when you will be doing the data analysis, or when you will be computing data analytics, how you will be deal with it, how you will be able to handle that particular situation. This is important thing. There are many ways, there are many approaches through which we can handle the missing data case. It's up to you. It's up to the problem. It's up to the data. Might be if you have millions of records, and maybe in few of the records, some of the column values is actually missing. You might just remove those tuples or those records. But if the data itself is very small, or comparatively much smaller than the other case, then you might not be interested in removing it. You might want to basically fill those missing data with those records which have values for that particular column, and the remaining value is quite similar to the values of the missing value tuple. Okay, so in some cases you replace with the average of the same group. In some cases you replace with the minimum of that group or maximum of that group, or maybe the global average or the global minimum or global maximum of that group, or maybe the value like I already told you that that the record which have basically missing value in that particular column is how close to other tuples. So those tuple which is very close to the to this tuple which have missing value, so you will be picking or you will be selecting the value from similar tuple and replace the missing value with the values of that particular column value. Okay, so in general, what are the possible strategies? You might ignore the record, the record which have missing value in one or more column. You might remove or ignore that record, or you can use a global constant to fill in all the missing values. So you have decided a global value for that particular column, and that value will be used to replace all the missing values in that particular column. This is the second technique. First technique, you can remove the complete tuple which have missing values in one or more column. The second approach is basically you can decide a global constant, and you just need to basically put that global constant into all the missing values of that particular column. Okay, maybe you can perform imputation, or maybe you can use some more advanced technique like Bayesian formula. Okay, like maybe you can use a decision tree, or something like in general you can use some inference based solution to replace the missing value with some other value suggested by inference. Okay, so you can use inferencing to replace the missing value with the one suggested by inferencing rule, maybe some Bayesian formula, or maybe some decision tree. Okay, so these are the ways through which you can handle the missing data. The next problem which we can deal with, we have to deal about, is smoothing noisy data. So again, this is a problem. Unlike the previous case which is handling missing data, in this case data is actually available in the column, but somehow the value is not appropriate. Maybe one of the reason might be again the outlier case. Maybe if all the students, if for example in your data science course, out of 100 all the students have around in between 70 and 90 marks, and somehow one of the students is basically just have 5 marks. So you will be like, okay, that the student does not have performed well, or maybe he was not interested in the overall course. So that might be the reason that he actually achieved only 5 marks. But again, you have to investigate. There might be the reason that the marks will be like 75 or 85, and somehow during typing someone has basically just missed to enter the first number and just entered the 5 value. Okay, but the variation is quite high, quite large actually. It actually create problem in the data, because the range, if you just skip this value, the range is from 70 to 90, because everybody has actually achieved marks between 70 to 90. But due to this case, the range become 5 to 90. The whole change in the range. So one of the reasons is one of the ways actually you can just replace this particular tuple or this particular student data from the overall data, and it resolves your issue. The other way is basically somehow you can take, again, like you can take average of all the students. So maybe 70 and 90, the average will become 80 might be, and you can just replace it. But you cannot able to do it blindly. Mind it, there's no specific techniques to deal with it. You have to analyze, you have to investigate the data, and only then you can able to either eliminate or keep that particular tuple. If you are keeping that tuple, do you really want to keep that particular value, or you want to replace that particular value with some other value, some average value or some max value, some mean value or something like that. Okay, so this is basically a very important thing that you have to perform smoothing of the noisy data, because even a minor value can create a real problem. For example, for human, a 99.4 Fahrenheit temperature means you are fine, and 99.8 Fahrenheit means you have a fever. And if our storage system represents both of them as 99 Fahrenheit, then it fails to differentiate between healthy and sick person. You know it very well. This is basically the time when we are actually facing COVID problem or COVID virus issue, and in every organization, and even shopping malls, you first have to go through some temperature sensing device, which will actually detect whether the person is appropriate, and they should need to allow him to enter into the building, or they need to stop him, okay, based on temperature. Here, just again, here in the temperature case, the variation is just very small, variation in just points, but actually it creates problem for the person. I just need to recall again, 99.4 and 99.8, just 0.4 difference, but 99.4 means person is normal, no temperature, but 99.8 means it's a temperature. Somehow basically your system is rounding off to the next value. Like in this case, for example, in this case, for example, it will become 100, and if it is rounding off to the previous value, then it will become 99. Both of the that might be possible that you have used a data type that actually causes this problem, and this will not create any problem if the temperature is less than 98, because in that case, whether it's go upside or downside, it will remain normal. It will remain normal temperature. But in this case, it will create problem in both of the cases. If 99.4 and 99.8 both become 100, then both will be detected as a person which is actually facing temperature or fever. But okay, so again, false positive. One is true positive, other is false positive. True positive, again 99.8 is actually temperature, so 99 is actually temperature having a fever cause. But 99.4 is actually not a fever problem, but due to the rounding, it become 100, and it will be detected by the system as this person is also facing fever problem. So false positive. If somehow it's actually round off to the previous value or truncate to the previous value, like both become 99. In this case, 99.4 become 99. He is actually normal because of 99.4, and after becoming 99, it remain normal. But 99.8, when it round off or truncate to 99, then it means that it will also become a normal case. So the person will not detect it as a person who is actually facing fever problem. Again, here it actually come under the false negative case. Means he is actually facing fever problem, but due to this system it actually detected as a normal person having no temperature or no fever case. Okay, so that's the problem. So again, noisy data really create problem and for the system. So we really need to take care of noisy data along with the missing data and so on. Okay, so this is basically very important step, and we have to take care of it very carefully. And remember, there is no one approach or there is no one fixed technique through which you can handle the situation. However, you can try multiple techniques, multiple approaches to deal with these type of problem. And remember, this type of problem is quite frequent. It's not basically that it never occur. It usually occur, and you have to deal with it. As a data scientist, you have to deal with it. You have to basically, handle the situation. In data pre-processing, there's another phase or step, you can say data integration. Again, this is very important. If you have ever worked with data warehouse, you might already aware it, or you are already aware of this concept that in data warehouse, you have to perform data integration. You might have multiple source system from which you have to retrieve data. You have to make a schema which cater or structure of all the source schemas. Okay, so this is again and you remember basically there's a phase which is known as ETL, extraction, transformation and loading, or extract, transform or load, whatever you call it. Okay, so in extraction or extract phase, you have to extract data from multiple sources. In transformation, you have to convert data from different format, different structure, different types into one consistent type. We generally call it a single version of the truth. And once you're done with the transformation, then you are able to load into the data warehouse. So first you have to extract from multiple sources, then you have to transform into one single representation, and then you can able to load into the data warehouse. So this is an example of data warehouse. So similarly, data integration means if you have data from multiple systems or multiple sources, each one of them has its own representation, even of the same attribute or same column. So you have to convert from different structure, different format or different type to one single type. Okay, and only then once you have performed integration from multiple sources, then you can able to move on. Okay, so just take one more example. Like in one system, gender is represented as 0 and 1, 0 for male and 1 for female. In another system, gender is represented as M and F, male and female. And in the third system, the gender is actually represented as full MALE, male, and similarly the female, FEMALE, female. And in fourth system, might be you are just using Boolean. Gens true, and false means female, something like that. So it's your representation. But when you are getting data from all these sources, you have to convert into one single representation. Might be you will convert all these into M and F. So it should be one single representation. You must need to integrate. So in data integration, combine data from multiple sources into a coherent storage space, like data from multiple databases or files, as we have discussed already about it. Maybe you want to definitely create a schema integration by combining data from multiple sources and make you can say a combined schema or a global schema which is actually able to store data from all these resources. So in data transformation, we want to transform data into some consistent and readable format or readable structure so that we can easily able to process this. For example, smoothing it means, again, as we have already discussed in data cleaning, that we want to remove noise from data. Aggregation, we might be interested in summarizing data or constructing a data cube. Okay, so if we are constructing a data cube, we might have basically different we might have basically data at different levels, from summarized to generalized. In a similar way, you can talk about generalization. In generalization, we can create a hierarchy from most summarized to most generalized. So at different level, it may go from low granularity to high granularity, or you can say from high granularity to low granularity. Okay, and it actually depend on levels. Okay, you might be the case that you have data, day-wise data, then week-wise data, then month-wise data, and then maybe year-wise data. So this is another way. We need to another option in data transformation. We generally need to perform normalization. We normalize our data, and it is very important. When we will be developing our machine learning model, then we will realize it that if you skip data normalization step, then your model will not be appropriate. Okay, so you need to normalize. What is, by the way, normalization? For example, one of the attributes, for example, age, and the other attribute is actually your salary. So salary may vary from maybe 15,000 to maybe 1 million, but the age will only vary or range from 0 to maybe 100. So when you have different scales for different attributes, then some of the techniques that cannot be able to handle this diversity in range exist in these different columns or attributes. So we need to normalize it in same range. Means, for example, if we have decided like our range will only be between 1 or between 0 and 50. Let's take an example, 0 and 50. So we have to map our age from 0 to 100 into the range of 0 to 50. And similarly, our salary from 15,000 to 1 million will also map from 0 to 50. If we map both of the attributes in one single scale, then it is actually somehow comparable with each other. So we need to perform normalization. Okay. For example, scale to fall within a small specified range and aggregation. Some of the techniques which we are used, one of the technique I already explained actually, but like min-max normalization, like minimum value and maximum value. You have to project, you have to map whatever your the range of value of your particular column into a value which range from whatever minimum you have decided and to whatever maximum you have decided. So in our case, in our example, I have basically mentioned about 0 to 50. So minimum will become 0 and maximum will become 50. So all the values, irrespective of what will be the value, like 50,000 or maybe the 1 million or maybe the 5, all will be mapped between this 0 and 50. Okay. Then z-score normalization, you might able to recall from a statistic that you have a formula for z-score calculation. So you can use z-score normalization, and of course you can normalize by doing decimal scaling. So you can just scale by using decimal values. Okay. You might also able to construct new features. Means or you can say you might able to create new attributes. Both of them are actually correct. Okay, let's take an example. You have length and you have width. Okay, you have two attributes. You might want to construct another attribute or another feature, and which is actually might be area, which is length into width. It will construct a new feature. Again, not necessarily this feature will be useful for you or your model or not, but this is just an example that you can construct. There are many other ways through which you can construct a feature. For example, in computer vision or image processing, you have raw image in pixel form. Okay, in grayscale maybe a 2-dimension, and of course if you are talking about RGB, then for each pixel you have a vector of R, G and B. Okay, so you have just raw image, and you might compute many features like edges, like colors, like anything else. Okay, so there are many formula available, like bounding box, for example. Okay, so you can compute many type of basically feature from your data. So you have image, and by using different formulas you can create or you can compute features from that source data. Okay, so this is another option, that you can create a new attribute or new feature from your existing attribute or existing features. Okay, this is something about data transformation. Then we will move towards data reduction. Okay, yes, in some cases we want to reduce our data. You might heard about the concept of dimensionality reduction, in which we actually want to reduce the dimensionality of your feature vector. Dimensionality means you can simply understand that the number of features. Maybe you and number of feature means number of attributes. You might have basically 80 attributes or 80 features in your data set. Okay, and but using 80 features or maybe more features will be more difficult or more complex to develop a model. And somehow, in order to reduce the complexity, you want to reduce the dimensionality of the data, but you want to keep the most contributing feature intact in your data set. Okay, so this is basically data reduction. For example, you can use the PCA or principal component analysis, through which you can basically map your data from one space to another space, one representation space to another representation space, but the new representational space is having the initial attribute are more contributing, more meaningful, then gradually you are moving towards the next attribute. Okay, so for example, if you have a 200 features and you perform principal component analysis or PCA, then it actually maps from one representational space to another representational space, but it will keep all the dimensions, but the dimension space is totally new. Means input have basically 200 features, the output space is also 200 features, but in the input representation space, features are actually mixed. Means that it means that it is not necessarily that the first attribute is more meaningful or more contributing. Okay, and second is basically less contributing than one, but more contributing than third, and so on. This is not the case in the input space. But what PCA will perform, it actually transform from one representational space to another representational space, in which the first attribute is the more contributing, the most contributing. The second is less contributing than first one, but more contributing than third one, and so on. So in that case, you might just keep 20 or 30 features instead of 200 features, but that 30 is maybe able to contribute 97 or 98 or maybe 99% of the information which as a whole are represented by the 200 features. So you are just losing 2 to 3% of the information, but you are able to reduce from 200 basically features to just 30 features, from 200 features to just 30 features, but you are keeping 97 or 98% of the information intact just by using 30 features. So in short, the remaining 170 feature has only 3% of information. So you are actually definitely you are losing 3% of the information, but in return you are able to reduce your dimension from 200 to just 30. So this is an example of data reduction. The last but of course not the least is the concept of data discretization. In many cases you have data in basically continuous form, and you want to convert into some discretized form or discrete form. This is required in many machine learning model as well. For example, if you are building a decision tree, then you have to have all the features in discrete form. It cannot be able to handle values or in continuous form or continuous variables. Okay, so you have to convert your continuous variable or continuous values into discrete value. Let's take example. If the salary of a person, or you can say the range of value of salaries from maybe 15,000 to for example 4 lakh rupees. In that case you might be basically transformed into 3 different categories, like low salary, like medium salary, and high salary. So it is up to you how you will be basically creating the range for each discrete value. But let's take an hypothetical example. You might basically take 15,000 to maybe 80,000 as a low salary, then then from 80,000 to maybe 2 lakh rupees as medium salary, and maybe from above 2 lakh to 4 lakh you will be like high salary. So low salary, medium salary, and high salary. So the whole bunch of range of values from 15,000 to 4 lakh rupees is transformed or converted into 3 discrete values: low salary, medium salary, and high salary. So in many cases, like even in age, in salary case and many other cases, we need to transform our values or continuous values, especially if you are real number, maybe 33.25 and 33.76 and 33.7672, and there's infinitely many values. So in order to better deal with these values, you might not want to use as these continuous real numbers. It is not always necessary to convert all these real values into discrete values. It actually depends on the situation. So it's actually depend on the situation. As I already explained about the decision tree, in that case you have to convert, you have to discretize, but it's not the case if you are using a neural network. So this is not always necessary, but in many cases it is necessary. When it is necessary, you have to convert this range of values into discrete values. Now let's take some example. For example, this is an example of data cleaning. You have this data, you perform some sort of actually cleaning process. You have putting this data over here, and this is basically some purification process where which you can actually clean your data, via which you can clean your input data. So you have clean, and once it is clean, it is ready for the next phase. So in the next phase we can now have clean data, which we can use for building models or further investigation about the data, or maybe to compute some data analytics. So in the next thing is actually about the data integration. So you can see over here we have different sources of data, maybe some spreadsheet, maybe some text files, maybe some databases. So you are actually combining, you are actually integrating all these data from different sources into one single structure, into one single database. So you have to make a schema or a structure which is actually capable to store data from all these sources after basically removing all the inconsistencies exist in this particular these particular data sets. So this is about integration. Of course, this integration does not only involve the integration of the data, but there might be other metadata associated with these data, and we might need to integrate all the additional metadata. I'm not just talking about the metadata which is about the structure of the data, but there are many other additional metadata which might be associated with these data sets. So we need to integrate all of them as well. Okay. So next, about data transformation. It is a very simple data transformation. There are many types of transformation as we already talk about, but this example is very simple, in which we are actually dividing all the numbers with 100. So like it become 0.17 and 0.25 and basically 0.39 and 1.28 and minus 0.39. So we are just dividing all these number. By the way, there is no minus here. This is 17, just to indicate that number is actually starting. Here it is actually minus, this is not minus. Okay, so just we have divided into all these number with 100. There may be in other case you might have want to divide with the biggest number, so that the value will only ranges from 0 to 1. In that case, might be here the maximum number is 128. So if you divide every number with 128, this is the 128 itself, so it will become 1, and rest of the number will become less than 1. So there are many possibilities through which you can perform data transformation. This is just one of the examples. The next example is actually about data reduction. Okay, so now you can see over here the as we already discussed about it, like dimensionality reduction. So now you can see over here there are total 200 attributes from A1 to A200, and total tuple from T1 to T200. But here you can see that I will be more focusing on this thing. Okay, so I'm in the column reduction. So now you can see after transformation only 120 feature or column will remain, and 80 is actually discarded from the data, or actually it actually reduces from 200 dimensions to 120 dimensions. So this is dimension reduction. If you just talk about, if you want to add why basically this is number of tuples, this is one of the reasons that we already talked about it. Might be some of the data has some missing values or some ambiguities or some noise, so we just eliminate all of them. So instead of 200 tuples, it will only become 150 tuples. So this is actually an example of data reduction, in which we actually reduce our data. By the way, if you are reducing tuples or if you are reading column, both of these are actually data reduction. But if you just want to talk about dimensionality reduction, okay, so if you just want to talk about dimensionality reduction, then this means we want to remove, or we want to reduce the number of attributes or the number of columns or the number of features. But all these things refer to the same thing. This is one feature or one attribute or one column, whatever you want to call it. So in this case, we have reduced the dimensionality from 200 to 120. However, in case of data reduction, it is also reduces the data. If you are eliminating some of the columns, if you are reducing the number of columns, This means you are doing actually data reduction in the broad concept. And this concept is also applicable in case of tuples. So if you are removing some of the tuples, if you are reducing some of the tuples, it is also come under the umbrella of data reduction. So either you are removing a column or either you are removing a row, both of them actually belongs to data reduction. But if you are just removing columns or reducing column, then it is also known as dimensionality reduction. Okay, so with this thing, I would like to basically conclude today's lecture. And in the next lecture, we will discuss about some practical example, and we will try to basically apply whatever we have learned in this chapter to solve some of the data pre-processing related tasks or problem using some data set. Till then, thank you very much.